All right. Start a 30-minute timer.
Okay, 30 minutes and counting.
Okay. What's this called? We're going to do a new exercise, moving zeros to the end. And I'm going to make a new one called zeros. I've got my server running in the background. That's going to send the code to the browser here, so I should be able to okay. What I'm doing is I'm practicing talking while I solve a problem. It's a skill that I need for interviews. Not just talking about what I'm doing, that's rambling. I need to talk about why I'm doing what I'm doing to expose my intent and thought process. So before I do anything, I need to be able to execute this code so I can get some sort of a feedback loop going. So I'm going to put this in here, make sure that I can send stuff here. I can. Cool. Now I can sort of TDD this. I don't like the var, so I'm going to change this to const, and let's make this a little more modern. There. So let's figure out what the question is. Write an algorithm that takes an array and moves all of the zeros to the end, preserving the order of the elements. So I'm going to get an array, and I need to understand the contract. I'm going to get an array in, and I'm going to return an array out. So very TDD sort of way to go. Okay, first thing, we get an array, we return an array. Now, I'm going to need to go through the array, and before coding, I want to talk about the design a solution. So I'm going to need to go through the array, find all of the zeros, and move them to the end. So we need to visit every part of the array. So we're going to need to iterate through it. As we iterate, we will need to move items. So do we want to make a new, we're gonna have to return an array. So are we gonna make a new array, or are we going to alter the existing one? The functional side of me says don't mess with that array, because somebody could have passed that by reference, and that would be unkind to do, even though they should not, or they should guard against that. However, just to be gentle, we don't want to mutate the array that's being passed in. Therefore, we are going to need to return a different array. So the two things we need to do are iterate this array and build out a new array. So the new array is going to be the result. Of course, result's not defined, so we define that. Now to iterate through the array, this is kind of side effecty, but we can just do array for each. This is the item. As we look through the array, we can build out our result. For simplicity, let's just say result push x. Now this is not going to actually change anything, but it's going to demonstrate that we're visiting each item and that we are building out our new result. Now we need to add a little bit of logic here to make sure that we're not just pushing it in there, right? So we to to sort of partition this into the numbers that are not 0 and the 0, we need to sort of keep track of those separately. So it would be good to have two different arrays, say the non-zeros and the zeros, and then at the end we can concatenate those together. I'm concerned about the operation time for that, but I think it is a good idea to get something working first, and then we can go back and optimize it. So we're going to visit each item in the array. We're going to have two arrays that we build out. There's going to be one with the non-zero and one with the 0. And at the end, we're going to concatenate those two lists, and that'll be our result. So instead of results, let's make this non-zero, and we're going to make another one called zeros. We're going to say if x is 0, zeros push x or 0. Otherwise, push to the non-zeros. And when we return, we're going to say we're going to return a list that is non-zero and zeros. Let's try that. Okay, that works. Let's see how it goes performance-wise. I mean, it works. I wonder if this is the best way to do it, though. So we're going to have to visit each item once here in the array, or when we first loop through. Now this destructuring is going to have to visit each item again. So I don't think that's optimal. Let's see, what else could we do? We could filter this list of arrays into our non-zeros and then just tack on a number at the end. So say we could go through and filter all of these zeros, keep track of how many we filtered out, either by counting or by comparing the length of the filtered results with the initial array length, and then sort of shim that by adding the zeros. So that means we would pass through once, and then we would just have a concat at the end. Let's try it just for fun. So we're going to say non-zeros equals filter return x not equal to 0. So this will get us the non-zeros. Now we'd have to figure out the length difference. So diff equals array length. And this will tell us how many zeros were removed. And then we're going to have to add that many to the end, which might be weird. I think this might make it more complicated. But just to demonstrate, let's see. You could say while zero's length is less than this diff, then we need to add another. And then we could return non-zero cat zeros. Let's try that. That's not right. What's different? It expected 1, 2, 3, 4, 5, 6. 4, I got 6. Oh. Wait. So let's see what happened. We did move them to the end, but we added too many zeros. So the difference I have an equal sign here. Let's try that again. Okay, so that works. Instead of looping through here again, we're already at this point. We could keep the condition here and just have the side effect. So x, if x is equal to 0, then we could push it into here. I would like this to not be tied to zeros. It could be like any sort of whatever we want to move later. So this might abstract it a bit, so it's not committed to being zeros. We'll change this to put at end or just something so it's a little more explicit. So at this point we could we're sort of killing two birds with one stone. We're saying if it's not 0, go ahead and build that out. So now we can have the same results, but we don't have to have as many loops. Let's try this. Looks good. This logic is redundant now. We could make it, we could say, change the logic to something more general, move to end. If that's the case, in this implementation, it's going to be x is equal to 0. So if move to end, then we're going to push to the end, and then we're going to return not move to end, which means keep it where it is. So we're going to say, change this to put at front. Everything's unchanged, and think a little bit more explicit about what is happening here. It's very side effecty, for sure, but you know. So I think this is a pretty good way to do it. Now we could probably go through this just in one pass and hit, like, just walk through the array, and if it's a 0, move it to the end, and we'll have, that might get us some benefit to go through doing it just once, looping through just once, but it would require juggling the index and understanding as we change things that we need to move it, and then we need to understand that we're mutating the array that we're looping through, and when we move something to the end, we would have to adjust the sort of end that we're walking through. So that would make it more performant, perhaps, because we wouldn't need to do the concatenation at the end, but we would need to. It would be a little more complicated because we'd have to keep track of those indices. But how much time do we have? We have 15 minutes. What the hell? Let's do it. Let's see. Get status. Solved 0.
It's
So
10
I'm
hours.
going to add a variation here. So what we're going to do is we are going to build out the array, and we are going to loop through in one pass. So let's just do some sort of pseudocode here. We're going to have the result array. We're going to walk through the array. If 0, well, if it's not 0, add to results. If it is 0, we're going to let's see. I guess we have to add it to the results either way, but we're going to have to keep track of where where our insertion point, right? So we've got this list. Okay, and results going to have like some values here, our insertion point, and some values here. So as we add things, we're going to have to add them to our insertion point. So basically, this smells like a tree, like a binary tree or something. But basically, we're going to say, is this value, does it go on the left or the right? If it goes on the left, put it in here, insert it at the insertion point, and then move the insertion point to the right. If it goes to the right, insert it. I mean, these are all the same, so it doesn't really matter where we put it. An algorithm takes from all the zeros to the end, preserving the order of the other elements. Okay, so if we put it in the right, it doesn't matter if we put it at the end or if we put it here. But for consistency, we'll say anything going in to the right is going to go here. Anything going to the left is going to go here. So we have here, so the insertion point, we're just going to say I is equal to 0 for now. When we add left, we're going to insert at 0, and then the I is incremented. When we have when we have I equals 0, add right really just means insert at 0, and I stays the same. Okay, so we always insert at 0. So yeah, this shouldn't be too bad. So again, we're going to say set up our array that's going to hold stuff, and here we're going to return the result. Our insertion point is going to have to, I'm just going to call it I. It's going to have to move, so we need to make it we can't make it a const. How are we going to know when we're done walking through this array, huh? Well, that's easy. We're just walking through. So array for each. Now, at this point, we're going to say insert left or right. Either way, we're going to insert at I, and then if it is left, increment I. So insert left or right, what does that mean? That means x is equal, let's see, insert left means that x is not equal to 0. So now that we know that, we are going to say results splice the index. We're not removing anything. The new value is x. There we go. We have inserted it into the appropriate place. This is probably expensive though because we're splicing. Just this is for fun though. So anytime we splice, we're technically anything on the right of the insertion point is going to have to be bumped over. So there's a cost to that. I guess worst case scenario. I'm not sure how it compares to what we were doing with the concatenation, but I'm not optimizing this right now. So anyway, so we're going to always insert it here, and then we're say if it was insert left, then we also need to increment I. Now that oh, because I put. Let's give it a test drive. It works. Let's try it on all the data. It works. Now, I feel like this is nice because we're looping through just once. Instead of for each, we could do a primitive for loop. But then we would have to maybe keep track of I and our current index separately, which might get more confusing. I think this is fair though. This is pretty easy to follow. The way it works, right? So let's say alternate solution for moving zeros. So is there anything that we can do with the, I don't know, I'm not going to just waste time here. I think I've accomplished my objective of talking about what I was doing while I do it. And this looks good. So thank you for participating. See you later.